Howdy everybody, Mr. Miles here, and today we're going to learn about definite integrals. Okay, so let's recall when we were finding the derivative, what the derivative did for us. It would find the slope of any function at any given point by finding the slope of 2 points and making the distance between those points change in x approaching 0, becoming infinitely small. So when the slope between these 2 points was, or the distance between these 2 points was infinitely small, we would find the slope of the function at any given point. Now the integral is going to do something neato as well, and what it's going to do is find the area between a function and the x-axis Okay, it's going to find the exact area between the function and the x-axis. All right. Now remember, with Riemann sums, what we did is we would estimate that with the area of rectangles. We add them all up. So for instance, we had 4 rectangles using the midpoint Riemann sums. We would have an estimated area of 4.625 when in actuality the area was 4.6 repeating, or 4 2/3. And the more rectangles that we added up the area of, the more accurate the estimate was. So for instance, there's 10 rectangles, getting closer. 50 rectangles, closer you still. 100 rectangles, closer. 500 rectangles, even closer. Okay? But what's going to happen with the integral is it's going to take an infinite number of rectangles, add up the area of all of those, and give us the exact area under the curve, the exact area between the curve and the x-axis, by adding up the area of an infinite number of rectangles. The antiderivative of the integral adds up those areas. Okay, now, just to show you that it does indeed work, and I'm not lying to you, we're going to find the exact area under the curve f of x equals x plus 1 from 0 to 3. Okay, now you can see right here that this is a nice straight line, so we can find the area just by using our geometric knowledge and breaking this up into a rectangle right here, and a triangle right here and a rectangle right here. Add those two together, and that will give us the area under the curve. So this first one is a triangle. Area is 1/2 base times height, so area would be 1/2. The base is 3 units. The height is 3 units. So the area would be 9/2. That gives us the area for this triangle right here. Then the area of this one is a rectangle, is base times height, or 3 times 1, which would obviously be 3 units. Okay, that gives us the area for this right here. So if we added these two together, 9/2 and 3, and let's get a common denominator, 9/2 plus 6/2, the area would end up being 15/2 units squared. Okay, now let's try it with integrals. Okay, and the way we do it is to find the area under the function f of x. We take the antiderivative of that, and once we have the antiderivative, we plug in our ending point minus our starting point. So for the one, let me give you a second just to look at that. Okay, so we put in our function right here, take the antiderivative, we plug in the ending point on the x-axis that we're looking at, the region that we're looking at, the interval, and then minus the antiderivative, substituting in the starting point. All right. So right here we're looking at between 0 and 3. All right. We're going to take the antiderivative first of x plus 1, which would be add 1 to the exponent. Whoops. Add 1 to the exponent. New exponent goes to the denominator. Coefficient of 1 goes up top. Plus the antiderivative of 1 would be x. Now instead of being plus c, because we're finding a definite integral, what we're going to do is the notation is going to look like this. It's going to be from 0 to 3. Okay? And first thing what we're going to do is we're going to substitute in this antiderivative, 1/2 x squared plus x, substitute in 3 for x. So we get 1/2 3 squared plus 3, and then minus, take the antiderivative and substitute in your starting point, which would be 0 in this case. Now obviously you can see that this is going to be, I'll put the parentheses to show that this is the first one, this is the second one. Obviously you can see that when you plug in 0, you're just going to end up with 0. But this is going to be 1/2 times 9 plus 3 minus 0, which is 9/2 plus 3. Let's get a common denominator, which would be 9/2 plus 6/2, which is 15/2 units squared. That's going to be the area under the curve x plus 1 from 0 to 3. Let's see if that matches up with what we did earlier. Ta-da! 15/2 units squared. Yes, indeedy. So it does indeed work. Okay. So all you do is you take the antiderivative of the function given as such, and then we go from our starting point, which in this case was 0, to 3, find the antiderivative, substitute in your ending point, then minus, substituting in your starting point, and that will give you the area under the curve. Awesome. All right, let's find the exact area under the curve from -1 to 2, which would be from here to here. Okay. So we're going to find the exact area of this by using the integral. And it will take the area of an infinite number of rectangles, add it all up for us, and that will give us the exact area under this curve. All right, so what we're going to do first is find the antiderivative of x squared plus 1, which would be add 1 to the exponent, new exponent goes down here, coefficient of 1 goes up top, plus antiderivative of 1 is x, and we're going from -1 to 2. All right. So what we're going to do is first we're going to substitute 2 in for x into our antiderivative. Plus 2, that's our first one. Minus, then we substitute in -1 in for x. Plus -1. Now be careful with your negatives on all this, because it will indeed bite you in the butt if you don't get it correct. So this is going to be 1/3 times 2 cubed, which is 8, plus 2. Minus 1/3 times -1 cubed. -1 cubed is -1, so -1 times 1/3. I'm just going to go ahead and write it out. Plus -1 or -1. So we get 8/3 plus 2. We distribute this. I'll go ahead and work it out. So that's going to be -1/3 minus 1, which would be 8/3 plus 2. 2 negatives distribute this negative to each one of these, so it becomes plus 1/3. 2 negatives become a plus 1. And now we have to have a common denominator of 3. So it's going to be 8/3 plus 2, which would be the same as 6/3, plus 1/3, plus 1, which is 3/3. And we get 14, 15, 18/3. Okay, that would be that integral right there. And if we're talking about the area under the curve, that'd be 18/3 unit squared. That is the exact area under the curve from -1 to 2 right here. The exact area of that region, that figure right there, is 18/3 units squared. Okay. All right, so let's do a couple more. We're going to find the exact area of the curve from 0 to pi. Let's go ahead and do some trig. I know y'all are jonesing for some trig. So we're going to find the exact area under the curve f of x equals sine of x from 0 to pi. We're going to find out what that area is right there. Okay. Alrighty. And just a heads up, if it's area underneath the x-axis, such as this right here, this is going to be a negative area. So if we found from 0 to 2 pi, this would be a positive, this would be a negative, these would be exactly the same area. and you would end up with an integral value of 0. But we're just looking at it from 0 to pi, find the area of this figure right here. All right, so the antiderivative of sine of x is negative cosine of x, and we're going from 0 to pi. Now with trig, you have to be careful, because you might say, oh, 0 is just going to be 0. Not the case when we're talking about trig. So it's going to be negative cosine of pi. Okay, it gives us the first one, minus negative cosine of 0. That's going to give us our area under the curve. So remember, let's look at 0 has coordinates of 1, 0, and pi has coordinates of negative 1, 0. 0, this is pi. Remember, cosine is your x value, sine is your y value. So this is going to be negative cosine of pi is negative 1, so negative 1 minus negative, the cosine of 0 is 1. So we get 1, 2 negatives plus 1, which is 2 units squared. So the area from 0 to pi under f of x equals sine of x is exactly 2 units. It's exactly 2 units. Okay. All right, let's look at this one. So the antiderivative of cosine of x is going to be sine of x. Antiderivative of 1 is x, and we're going from 0 to pi. So once again, we substitute in pi, so it's going to be sine of pi plus pi minus sine of 0 plus 0. And that's the worst circle I've ever seen. Here's 0, here's pi. It's a slate, I promise you. I don't draw circles using that. Terrible. X is cosine, y is sine. So the sine of 0 is 0 plus pi minus, I'm sorry, sine of pi, my bad. Sine of pi is 0, and then plus pi minus sine of 0 is 0 plus 0. So therefore, the answer would be pi units squared if we're talking about the area. Okay, if we're just saying the integral, such as this, if we're just evaluating this, the answer would just be pi. Alrighty, and let's look at one more. All right, now first off, in order to be conducive to the mechanics of calculus, we're going to change that root x to x to the 1/2 over x, and because we don't know a quotient rule like this, what we're going to do is we're going to split this up into 2 separate terms, each of these over x, so x squared over x plus x to the 1/2 over x, and remember when you are dividing like bases, you subtract the exponents, so this is going to be just x, and it's the same as 2 over 2, so that's going to be plus x to the negative 1/2. Alrighty. I'm going to take the antiderivative. The antiderivative of x is going to be 1/2 x squared. Probably get used to that. You add 1. One that's already a 1 there, so you add 1 to get times 2. New exponent goes down here. Coefficient goes up here. Now this one we're going to add 1 or 2 over 2. So we get x to the 1/2. That's going to go, new exponent goes down here. And 1 goes up here. And plus. And we're going from 1 to 4. And let's go ahead and simplify this. So it's going to be 1/2 x squared. And 1 over 1/2 ends up being 2. 2x to the 1/2 from 1 to 4. So first we're going to do is plug in 4. And remember, x to the 1/2 is the square root of x. So it's going to be 1/2 4 squared plus 2 times the square root of 4. That's going to be our first one. Minus 1/2, to put in our starting point, which is 1 squared plus 2 square root of 1, which ends up being 1/2 of 16, which is going to be 8, plus 2 times the square root of 4 is 2, so 2 times 2 would be 4, minus is the first one. 1/2 of times 1 squared is going to be 1/2, plus 2 root 1 would just be 2. So you end up with 12 minus 1/2. Distribute this negative minus 2. Let's go ahead and get a common denominator of 2. So we get 24 over 2. Oops. Do that thing again. Hit this button. Minus 1/2 minus 4 halves, which will be 19 halves. Alrighty. Y'all have a good one. The worksheet is on its learning as well. So good luck, everybody. Hopefully this made sense. And I will see you tomorrow.